rather embarrass you. So you have to there by
Perfect. Okay. And what time does it finish? 12:30. I think we'll be fine. I've been through it a few times. I was saying to Alex, if Heloise took this class, she should be able to pass it. She's heard it enough.
I'm glad it's not just me.
She wasn't listening, though.
Just keeps volunteering to make my slides more interesting.
I'm sure when...
More colors, some background.
That's funny. I'm sure when a show comes, he'll have memes in his slides. He always has memes in his slides. Yeah.
I've never heard either of you. I've heard you speak now from the background.
She speaks really well.
Is he still on the message?
No. The way to argue with a show is just to let him talk. I completely... Yeah, it's perfect, right? You know, you plant a seed, he disagrees with it. You just have to sit back, and then eventually comes around to it, and then you tune back in. Of course, you don't really tune out.
Let's get started. Good morning, everyone. We're going to get started. So it's a pleasure and an honor to introduce today's guest speaker. We have Rob Shakir here with us, and we really couldn't have found someone more perfect to lecture on this topic. So Rob is one of the key technical leads at Google's global networking team. This is the team that runs the entire wide area backbone network that Google operates. But he's also responsible with other folks in doing the technical evaluation of router equipment and deciding what Google runs in that wide area network backbone. He's also one of the lead authors on OpenConfig, which is pretty much becoming the de facto standard for how you configure and manage routers in the network. And also, that's a long list of achievements, one of the main authors on segment routing, which is probably the cutting edge in routing protocols that's for the IETF standard, which is, I think at this point, is standard, right?
Yeah.
Oh, right. So without any further delay, thanks, Rob, for being here, and welcome.
Thank you very much. I think it's funny. I really wish that at some point I'd done a computer science course and been taught about routers at all, but I'm going to talk about something that I've been working on for about 20 years, which is a large number to think about, and just kind of share, I think, some of the background and some of the information about things that I've spent a lot of my life thinking about, but other people might not know about or think that it's just a box in the corner of their apartment that deals with their broadband. So we'll start out, and I think you've seen this picture before. What's the purpose of an IP router? An IP router is there to be able to take a packet, figure out where it should go, and route it along the right link. So, in this case, a packet comes in with a specific destination address. It's got a specific link it needs to go down. And so we're going to talk about how does it actually do that? What's the, look at what a router does and talk a bit about, and I'm just going to disclaim this. I say router, I'm British. In America, they say router. I'm not going to try and say that. That's something that cuts grooves in wood in the UK. So I'll stick to the one that moves packets. So it's things that perform IPv4, IPv6 lookups against the destination IP of a packet. You'll remember or be talking about that they run routing protocols, which is how they learn about routes that are going to be, tell where things are, where to route towards. And routes are I also say route, not route. Again, British disclaimer. Routes are sets of destination IP addresses. So today we're going to talk about what is a router. And to start with, we're going to take a little bit of a step back. And this is, the things when we start talking about a router can often be quite dry and not really know how it fits into the real world. So these are a couple of photos I've taken, or I think maybe I took the one on the left and not the one on the right, sorry. And we'll talk about a little bit about what makes up the internet. The internet is really just a bunch of networks connected together. And what's connecting those networks together is routers. And when we deploy those routers, we put them into some facility, like these ones. They're buildings that are specialized to have the power, the cooling, and everything that we need to be able to put routers in there and interconnect with each other. So when Google interconnects with Comcast or Google interconnects with Verizon, that's in a building like this, most likely. And these buildings, if you go into them, it's just racks, floors and floors of air conditioning, racks that contain these routers that are what we actually use to build the internet to kind of connect things together. And so here's a couple of photos. These are not these are relatively historical photos because these are the ones that I can share. They're from a network that I worked on a few years ago. And this is what a router looks like. It's we'll come back and kind of talk through what a router is, and we'll come back to one of these photos and have a look and say, okay, how does that map? And what is a router really? Well, it's just a computer that is really specialized for forwarding packets. And there's many different sizes of that router. These are two different ones. You can see that one's got horizontal slots, the other one's got vertical slots. There's various reasons that they look a bit different, but really at the end of the day, that's what a router is. It's just a computer that we've designed to be really specialized to forward packets. And they come in different sizes. So, you've got everything from the small blue thing here that might be a home router that's got Wi-Fi and it's got a small number of ports. We might have things that are one rack unit tall. That's the kind of unit that we use to measure things inside a cabinet. Is a rack unit. It's a couple of inches. And you'll see here that this one is a one rack unit. We might call it a pizza box because it looks like a pizza box. And then the larger case on the right-hand side of this slide is something larger that has more line cards. And the dimensions that we have in terms of these routers, we kind of measure the physical size. We also think about, well, how many ports does it have? If the whole point of this thing is to forward packets and interconnect, then it really needs to have, how many ports, how many times can I interconnect with other systems? And then the bandwidth. The bandwidth is how much capacity does this router have to actually forward packets? And obviously that's a really key thing. As we're looking at a certain data volume, we need to know, well, how much data can we put through a specific router? And so if we think about the definitions, how we kind of talk about routers, we talk about them in these different dimensions. So, we have the number of external ports that's there. There might be internal ports and things that are used to connect bits of the router together, but we don't think about those. We really think about the ports on the outside. And sometimes, in the industry, they'll be called revenue ports because the vendors that you buy them from, they're the ports they can actually sell, they can actually charge you for. Then each port has some form of speed, has a speed of that port. We often refer to that as the line rate. So sometimes ports run at different speeds. You could have a port that was 100 gigabit that was also able to run at 40 gigabit or also able to run at 10 gigabit. But these, when we're talking about the capacity of a router, then we think about what the line rate, what's the maximum rate of that port. And then there's the capacity of the router. So the capacity of the router is just the number of ports times by the speed of those ports. So if we think about this kind of small little router here that you might have at home, maybe it's got a couple of different types of ports. Maybe it has 400 megabit ports. That gives you 400 megabits of connectivity there. And then you might have one gigabit port. So that gives you a gigabit of capacity there. So the overall capacity is this 400 megabits plus a gigabit. So it's a 1.4 gigabit a second router. Probably can't actually do that because of how it's forwarding, but that would be the capacity of it. If we think about what we actually deploy in a network like Google's today, this is an 8-slot system. It has 8 line cards. We'll come on to what a line card actually is. Each one of those has 36 ports. So the number of ports here is 288. We have 36 times 8 ports. Each one of those ports can run at 400 gigabits per second. So the router capacity we have today is those 288 ports times the 400 gigabits, which is about 115.2 terabits per second, which is a lot more than your home router, but these numbers continue to get kind of interestingly bigger. And why do they get bigger? Well, in this same size of physical deployment, we don't increase the number of ports. That's kind of limited by the amount of space we have on the front of the slot. There's only so much physical space, and if we have to plug an optical module into it, there's only that much space for those ports. So it stays at 36 ports. We still have the 8 line cards. We didn't make the chassis any bigger or smaller. But we can then put different line cards, different modules into it, to rather than run at 400 gigabits per port, we can run at 800 gigabits per port. And that gives us a doubling of the capacity, 288 times 800 gig now, and looking at about 230 terabits per second through this router. And these numbers change over time. So this is a view that we put together a few years ago in Google, which is now sufficiently old that I can share it. But if you see here, we started out with these systems on the left-hand side of the slide. The Juniper system there is 1.7 terabits per second. Then we got bigger routers. So the one along, it was a physically larger. It had more line cards, which means it had more ports, which then increased the capacity. Same again, we increase the number of ports and the capacity goes up. But you'll see here that really at some point we run out of space. A rack is about 7 or 8 feet tall, depending on what exact size you have, and that's about the amount of physical space you get to put things in. There's then a physical size of optics, so that's how many ports you can get on each line card. But there's also some constraints around, like, well, how much power can I put into the rack? Some of these systems will be pulling 50 kilowatts of power. So there's a significant power draw. And you also, got all that power going in. Where's it going? A lot of it's going into heat, so you have to cool it. So a lot of the physical constraints that we have about how big a router, what the maximum capacity is going to be, is really around how much can we fit into that rack. And you'll see here that, the numbers go up, but the things don't necessarily get much bigger. Even between this Cisco device, the ASR 9000 and the Arista 7500, the thing got smaller, but the capacity went up. And that's the result of when we increased the speed of the ports. So there we went from a 10 gigabit base system to a 100 gigabit base system. And as we go to 400 gigabit systems and 800 gigabit systems, as we kind of talked through on the previous slide, that's when we'll start, the capacity of the router continues to increase over time. Okay, so that's that kind of like the photos of what routers kind of look like. So let's talk about what actually is inside a router. So once we kind of peeled the metal skin off, what would we find? And we'll use this conceptual picture and we'll iterate on it a little bit to talk through what it does. So we have some chassis. That's the overall unit of router. It's the thing that collects all the line cards together. It's we would talk about a chassis having a capacity because the chassis is the overall router. That chassis has two different types of cards within it. It has a controller card, and then it has line cards. Controller cards are where the control processor, it's usually an x86 processor, probably running Linux, that sits in that device, and its job is to exchange routes with things, to do those control plane management plane software jobs, and program the line cards. The line cards themselves are the things that are dedicated to forwarding. So you've got the ports, the input and output ports on that line card. Input and output ports is the same set of ports. A port is bidirectional, and the same port can be the input and output port can be different ports on the same line card. It can be different on different line cards. The line card itself might have its own control plane processor, its own CPU, and that will be there to do anything that's local to the line card. Maybe it's managing whether links are up or down, or responding to any kind of local protocols that are running there. And then there's some way that we, once a packet's come in, we can interconnect to another line card. I'm kind of drawing it as a mesh here, where every port can talk to every other port. And then on the other side, we have more than one line card in the system. In some systems, or in the smaller ones, maybe they just have one. And then we have the output line card, which is doing the processing of packets before they're routed out into the rest of the network. And when we talk about routers, we kind of really talk about them in terms of planes. Like, that's the sets of functionality that the router implements. And so the first one of those is the data plane, sort of the real one that we care about, right? These are computers that we want to forward packets quickly. So really we care about, well, how is it forwarding packets? And that's made up of mainly the line cards. There's between 1 and 20 line cards in a system. Usually that's constrained by how big we can build the fabric, the thing that interconnects the line cards, and the physical size. At some point it's too difficult to fit. There's not enough space in that rack to fit more line cards in. And that helps you choose the capacity of a router. You can choose how many line cards the router might have. On a line card itself, you'll have some specialized hardware to forward packets. That's something that's designed really to do the packet forwarding. We'll go into a lot more detail about that. And then something that rather than having this full mesh of wires between every port, we want to have the line card is a removable unit. So we want to have something on the chip on the line card, on that thing that we can remove, that then packages the packets to be able to be transmitted to other line cards. And that thing that interconnects all the line cards we call the fabric of the router. So here we've got a fabric. There might be multiple fabric cards in a router that help that interconnection achieve the right bandwidth, help us have the right reliability. But then the forwarding chips and the fabric chips make up the data plane of the router, the thing that really that does the mean veg of the job and forwards packets. We then have the control plane. The control plane, I think, talked about a bit in terms of it gives you the way that you talk to other routers, the thing that runs the control protocols, the routing protocols, to be able to talk to other routers and figure out what routes to have. So it might be running BGP or an IGP like OSPF or ISIS, and it then exchanges those routes. It figures out what the routes we want to use are, and it's then responsible for disseminating those routes down to the line cards. So the line cards themselves don't really know anything about how to figure out what routes to take. What they know is how to forward packets along those routes. But the control plane is what figures out what routes we should forward down. And that's really pushing the forwarding tables down to the line cards. So its job is to go and take that external interaction with other systems and then program the line cards to make sure they're forwarding in the right direction. Alex?
How many line cards are in the chassis?
Between 1 and 20. So it depends on the kind of size of the system here. So you have the control plane is also responsible for making sure those line cards are consistently programmed, because we want to make sure that they've got the right routes. Everyone on the chassis kind of understands the same view of the chassis. Then something that doesn't get mentioned very often when we're talking about routers, but as Sylvia mentioned, I spent a lot of my, about the last 6 or 7 years thinking about a lot, is how we manage the chassis, the router. So we put the router in, we said, okay, it's got some control plane protocols, but who does it speak to? And then when we've got it running, then how do we know what it's doing? Like, is it dropping packets? Does it need to be repaired? So those whole sets of considerations are something that we would call encapsulated by the management plane functionality of the device. And the management plane kind of has two arms. One is that configuration. It's external systems or humans interacting with the device and telling it, okay, if you need an IP address on this link, it's going to be this. You should speak to this BGP neighbor. You should run OSPF on this port. Those kind of configuration operations are part of the management plane. And the other side is monitoring, or sometimes we call it telemetry, and that's where the router is telling us things about what it's doing. How many packets is it forwarding? Is this BGP neighbor up or down? Does this line card have a fault? And this is really critical for actually running the network, right? Because when we put this thing out in the ground and it's forwarding some packets, we kind of need to know that it's doing the right thing, so that if it isn't, we can repair the network. Otherwise, you have outages. So let's have a look at one of those pictures that I kind of put up earlier. And this is a real router. It's a few years old. Now it's a Cisco 7606. The 06 means there's 6 slots in it. 2 of those are control plane processors. 4 of them are line cards. So you can see here the white ones with ports on them. These aren't all fully populated, but you can see there that those are the line cards. That's where we've got all the input and output ports. Got these 2 gray cards at the bottom. You can kind of see they don't have very many ports on them. They have a few, but they've got things like a slot for putting a compact flash card in for storage. Those are the controller cards that we talked about. And then there's a bunch of other ancillary things that go into this chassis, which actually don't have to be really important. Like on the left-hand side of here, you've got a fan tray. This hardware produces a lot of heat, and so you want something that's removing it. On the back of it, there's a couple of power supplies. But that's what a router looks like. And if you kind of see, we kind of said, it's a computer that's specialized for forwarding. But we said, there's actually like line cards might have their own CPU. The control plane talks to the line cards. So actually, it's really like a set of computers that are all in this common metal tin that's used that are coordinating with each other to forward packets. And so they're a little bit more complicated than some of our pictures kind of show. But this is the how it might look in a real network. So let's just recap those definitions that we went through. So they've got the control plane. It runs routing protocols, allows the router to understand where to route packets. It's figuring out what should the router be doing in terms of forwarding. We've got the management plane that's interacting with systems or humans to configure and monitor the device. Increasingly systems these days, although historically these things were configured by humans typing at them. And then the data plane, which actually forwards packets. And you kind of need all of these things to run a router in a real network. If you can't manage it, if you don't know what it's doing, then you don't know whether it's doing the right thing, so you can't configure it to tell it what to do. Not a good thing. If it's not running the control plane, then it doesn't know where to route packets. And if it doesn't have the data plane, then it's not actually forwarding packets, so not that useful. So let's think a bit about specifically in the data plane. So specifically forwarding packets, what's important. And what types of different packets do we have? Now, and this is the thing you would expect every router to do. It's the key thing. You've got packets that are for users, for the packets that we're actually forwarding. And so they will come in on an input line card. We'll have some lookup mechanics that say, take that packet and route it according to some installed route. And then forward it across the forwarding chips, the fabrics, out to whatever other output port. These are the standard sort of packets that are being forwarded by the device. We also have control plane packets. So if you can imagine we're talking BGP to some other device, then there's some packets that are coming in, and they are to do with that BGP session. So they're actually packets that we need to pay attention to. And so in that scenario, the packet comes in, and it's not something that we should forward out. It's actually to us. So we then will send that packet from the line card up to the control plane. The control plane then deals with that and handles that in terms of it being a packet that we should listen to and takes whatever action based on that. And then there's a set of packets that are not really expected. So we have packets whereby it comes in, and there's things like the IP TTL has expired. And we need to do something to them, but we don't know necessarily, or we need to respond to them in some way. So we need to be able to tell the control plane, hey, you need to do something with this packet. We call those punt packets. So it's packets that we receive out a line card, we say, oh, we don't know what to do with this, or you need to do something with it, and we punt it up to the control plane to deal with it. So let's think about why this architecture. Clearly we've invented something fairly complex here, and so it's worth asking ourselves, why did we do that? If we think about the smallest Ethernet packet we can have, so the smallest packet we're going to link is about 64 bytes. Currently we're looking at 400 gigabits per second, which means we've got about 781 million packets per second per direction. Then we've got 36 ports on the line card, so we're now getting into 56 billion packets a second that we would need to look at per line card. In the practice, it's a little bit lower because not every packet is that small, but that's a lot of packets. It's a lot of things that we need to do. And it's not really achievable in a general purpose CPU. In general purpose CPU, we can probably do millions of packets per second. But we really think about this as the slow path. So, only when we have to do we rely on that. And otherwise, we want this forwarding hardware because we need to be able to scale to that number, to be able to meet that bandwidth requirement, to meet that kind of number of lookup operations. And so that's the fast path we would think about. And there's also another set of design constraints. These things can be lower power, they can be lower cost overall. And the order of cost of a device like this, the ones that I drew up, is in the millions of dollars. So we really do care about the cost. If the thing's going to be it's going to be more costly. It's much more expensive for us to build capacity. We can't scale to, you don't pay any more for your broadband bill as you use more traffic. And so you want to be able to make sure that you can manage the cost of these things. And actually, we really expect there's a cost efficiency year on year for the devices. So I'll pause here. Any questions that you'd like to ask, please we can dig into them now. And then we'll kind of dive in and look at some of the forwarding in more detail. Great. All clear. Or you're too shy. We'll see. So let's think about, when we're thinking about the user traffic, so we're thinking about forwarding these packets. Well, we need to think about what the input line card does. That's the first place that this packet is going to be received. And we kind of will step through a few things. First up, we have to receive that packet from another system. It comes in, it's either an electrical or an optical signal, depending on whether it came in on a copper wire or on a fiber optic. We have to do some decoding of the packet because it's been put into a certain format to be put on the wire. We do some functions around the IP header, so you have to think about things like decreasing the TTL or checking check some maybe options or fragmentation. Then we have to do the lookup, figure out where this packet should go. And the real key thing about this lookup is speed. We talked about that packet rate. Even if we increased that packet size away from the minimum to something that would be more typical for an average packet size, we still have very long to actually go and do that lookup. We've got packets arriving at a very quick rate. And we need to run quickly for each port, in the order of gigahertz per second to be able to even spend one cycle per packet on that. But we need to do multiple operations. We just said there's a bunch of things that we have to do with the packet in terms of lookup and check the IP header and those kind of things. So we have to think about how we're going to scale this thing. So this speed is a real key thing. Now, if we look at solutions for that, well, we could parallelize, right? We could say, okay, rather than have one chip go and do every packet, why don't we have just lots of chips? But then we start running into lots of power requirements. We need more physical space on the board. It produces more heat. And so that's why we've ended up with specialized forwarding chips. Those specialized forwarding chips are essentially processors that are designed to be really efficient in dealing with packet forwarding. And what they do is they compromise a bit on the flexibility of what they can do. You can't run a general purpose program on these chips. You can only run things that are kind of within the constraints of packet forwarding. And we have some programmability in some chips, in some we have none, but they have that really limited feature set. And then we say, well, if there's anything we can't do in that limited feature set that we have, well, that's what the control plane general purpose processor is for. So we then say, well, that's why we want things like the punt traffic flow, because we want to say, well, we couldn't implement this in the specialized forwarding hardware that we have, but that's okay because it's not every packet. And so we'll ask the control plane processor to go and do it. And that might be a distributed thing. There's a processor on the line card that can help us, but it's essentially outside of the key, the forwarding hardware. So if we think about that packet coming in, we kind of divide it down a little bit into how the layers are dealt with. So layer 1, the electrical or the optical signal here, we have some form of physical chip, a PHY, or a physical logical block at least, that's going to deal with decoding that signal from whatever it was on the wire in terms of physical signal into a stream of bits. Then have something that's doing the handling at the link layer, so the layer 2, where we're dealing with, there was an Ethernet frame that came in and we need to check the validity of that, do any Ethernet operations that we need. And these things are implemented in hardware. They're fairly standard. They're fairly constrained in terms of the things that they need to be. So we can implement these in hardware. We can do these at a fast rate. If we then sort of skip over the forwarding, because we'll spend a bunch more time there, then we have the fabric interconnect. We have a chip on the line card that's job it is to transmit packets to other line cards. And again, this tends to be a dedicated chip. It tends to be a different chip than the forwarding chip because it does slightly different things. It doesn't have complex routing decisions to make. It only has to figure out what other line card to make to send to. But it does things like split packets up so that they can be fairly sent across a lot of different physical traces, physical wires that are on the PCB and the chassis. So this once we've done with the forwarding, we know where that packet should go, then we will use this fabric chip to be able to interconnect to other line cards within the system. So then forwarding, like the thing that we really care about, the thing that the router is really there to do, tends to be broken up into a few different stages. The first of those is a parser. That we get a packet in. The packet needs to be read. It needs to be divided down into the constituent parts. So is it IPv4? Is it IPv6? Is there other headers around? That we'll talk about just IPv4 and IPv6, but there's other encapsulations that we look at, other ways that the packet can be formed up. So we want to break it down into the parts that we need to look at. Then here's exactly what the block that does the actual lookup, and then something that does any action. So adjusting the packet in any way that we need. And the basic things that you'll do there are things like the TTL, the checksum, but you might do more complex things in other networks. Where you're not just doing straight IP forwarding. You might put another header on or these kind of things. Now the actions in hardware kind of break down into two sets. Some of them are really easy to do in hardware. Like decreasing the TTL. It's pretty clear where we do it. We know it's a certain place in the IP header. We know that we just need to decrease it. Perfect, we can do that in hardware easily. Checksum, again, we know exactly what we need to do. More difficult where there's more flexibility. And so things like IP options, that gives us a problem where we have to think, well, what is the option? What should we do with it? And so we don't really have that much time, that many cycles, that much work that we can do per packet. So in these cases, we essentially try and avoid them. We can deal with them, but in general we say, well, there shouldn't be IP options. Shouldn't use them. We shouldn't put them into packets or allow them into the network. Some networks even filter them. And then fragmentation. This is achievable. So this is where we've got a packet that's big. That now with the link we're trying to send it onto is smaller than that. So we need to be able to break it down. And so this is achievable in hardware. We can figure out where to slice it and where to add the right headers. But we typically try and avoid it because it comes at some cost over and above just forwarding the packet. And so the way that this is achieved usually is rather than having some agreement as to what the MTU, the maximum transmission unit, should be across the network. And so on the internet, that's 1,500 bytes. Across internally to other networks, it might be much bigger. And inside people's networks, they might have their own agreement to say, we allow 5,000 bytes, we allow 9,000 bytes. There's various different values. It's sort of a domain local choice. But across the internet, we say, well, it's only 1,500 bytes. And this is fairly baked at this point. I think it would be an extremely difficult thing to coordinate changes to allow this to increase. But we do that by having these kind of mutually agreed standards gives us a way to be able to avoid this functionality and be able to keep the routers as efficient as possible. We want to focus on lookups, right? Lookups are where we really need to know what happens. And this is really the core functionality of a router. So let's dive into it in a bit more detail. So what is lookup in the end of the day? Well, it's figuring out where this packet should go. So we have to do and a lookup based on what output port is it. Now, the ideal would be that we do one lookup, and we get the forwarding entry that we need to do, and off we go. Which means that we need an exact match on the destination IP. We have the full IP that comes in, and we look it up in some form of map, some form of hash map. Okay, great. Off we go, send out this packet. Order one lookup, perfect. Other than, we have 2 to the 32 IPv4 addresses, we have 2 to the 128 IPv6 addresses. I'm not even going to try and figure out how to say the numbers, the IPv6 number, but they're big numbers, right? We would have to have a really, really large forwarding table with all these entries in to be able to do these exact matches. Equally, we have to figure out updating these tables and keeping them current. The larger table, these large tables are a lot of work to be able to keep current. And it sort of ignores a fundamental thing about IP addresses, which is the hierarchical. When I want to start a network, let's say I'm Google, I go to some internet registry, that's the people that assign IP addresses, and they say to me, hey Google, here's a big block of IP addresses. You go and figure out what you're going to do internally, we don't care. But here's your block. So give me an IP prefix of some size. And then internally I assign it, like maybe I go to the guys in search and I say, okay, this is your IP. This is your prefix, your IP prefix. I go to the guys in YouTube and I say something similar, and we kind of divide it down like that. But from everybody else's perspective, they don't care that I assign to search or to YouTube. They care that these need to go to Google. And Google can figure out where it should send the packets itself. So there is this kind of inherent hierarchy to the way that we have IP addresses. And practically, on the internet, we don't use any smaller blocks than 256 addresses. You cannot go and announce a smaller block than 256, a /24 prefix, to another internet network. It just won't listen to you. It'll filter it. Internally to networks, we do have to think about it, though, because you might have an IP address that is just one IP address, a /32 prefix, that we have to care about. But in general, we can think about how to exploit this hierarchy to give us more compact tables at the expense of lookup complexity. We can't just do this single lookup on the exact destination IP address now. We have to think about how can we look up something more than that. So, what does that work? What does that mean? It means that we have to try and find the IP prefix that matches the packet that we're trying to route, trying to forward. So let's look at this example. We've got Verizon. They are connected to AT&T. AT&T's got a bunch of downstream customers. We've got a packet here that's going to ABXY. So in that scenario, we're saying, okay, the destination of the packet is ABXY, and we want to go and look. Each network has to look in its forwarding table to say, well, where should I send that? And what it's trying to find is the prefix that matches that address. So Verizon here has A/8, then says, well, I don't know anything other than that should go to AT&T. AT&T then has inside, it says, well, I own A/8. But actually, internally to my routing table, I know that UCSF should have AD, LBL should have AB, and UCB should have AC. So in this case, AT&T does some lookup, and it says, well, what prefix in my routing table matches? In this case, it's something that starts AB. A /16 means that the first 2 octets of this address are fixed, so it knows that it needs to send it to the LBL next hop. So that's all very nice when there's just one route. But in practice, we have, in the internet, we don't just connect with one person and have this kind of tree structure. We have a mesh of different networks. All the networks interconnect to each other differently and can interconnect with each other in much more meshy fashion. So let's think about a simple case of that where here we have LBL that decides it wants to connect directly to Verizon. So Verizon now has routes that it's got this A/8 route that says, well, everything in it that starts with A, that should go to AT&T. AT&T's still got the same table. It's still got all those individual networks knowing where the downstream bits of the subdivisions of that prefix are. But now Verizon also knows that LBL has got AB/16, so it knows that anything that starts AB, those first 2 octets of fixed, should go to LBL. So in that scenario, well, we actually need to know not just what prefix matches, but what's the longest prefix that matches, so that we can send the packet to the right network. And this is longest prefix match. So essentially it says, take the most specific route that matches the destination of this packet. If it addresses if the address matches multiple prefixes, take the longest, the most specific. If it doesn't match anything, then we have a default route. So that's the route that says, well, if we don't know anywhere else, we'll just send it to this other next hop that might be able to deal with it. In some cases, we might not have a default route. If we don't have any route for the packet, we just drop it. We don't know where it's going. So LPM is the mechanism that gives us the way to do those lookups. So we'll spend a bit of time stepping through a few examples. So let's think about this pretty simple network here, where we have 4 different ports. Each one of them has got a prefix. They don't overlap. So P1 here has got the 201.143.0.0/22, and so on through the other ports. You can see there's individual ports mapped to each prefix, 1 per port. And so we want to find a matching route. So we have this packet that comes in. It's going to 201.143.7.210. And we want to figure out, well, where should that go? What port do we put that out of? That's the lookup mechanism that we're trying to do. So how do we do that? What we will do to start with is we start by converting the addresses to binary. Rather than thinking about this as 201.143, we'll think about it as 110, blah, 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 blah. So, and then we do the same thing in the routing table. And in the routing table, we have some concept here of wildcard, bits that aren't fixed. So you can see here where the hyphens are, where the horizontal lines are in the address. Well, our /22 has the first 22 bits set, but the rest of them are wildcard. That's what we said. The prefix means that prefix is this many bits are fixed and everything else is variable. So we convert the routing table into that form where now each one of these entries has the full specification in binary of what the mask that we should look at is. And if we kind of ignore the first set of parts of this address because at least the first 2 octets are completely fixed, and even the first half of the third one is fixed, and we think about these 3 bits, then what we start to do is we look at each bit as we go along. And we say, here, okay, we've got a 1. So look through our table and say, well, what matches here? Well, this one doesn't because there's a 0 in this bit position. But the remaining 3 do. They all match they all match the 1 here. So then we move on to the next bit. We say, okay, there's a 1 there. Now in this scenario, we look again, we say, we look through these prefixes and we say, well, this next one, this top one's got a 0 here, but we wanted a 1. So that's not the same prefix. Again, we look at the next one, something similar we can say, there's a 0 there. But this last one has a 1 here, i.e. we match this, and it's got a wildcard afterwards, so we know anything is going to match. So in a naive implementation here, we could say, let's check the incoming address in binary against every prefix that's in the table and select the longest one that it matches with. But note this isn't check the address against all prefixes and find the one it matches the most bits with. We really care that it's got a fixed bit string, the prefix matches, not just that these 2 prefixes have most in common. So we need to do this bit by bit comparison. And there we go. So now we want to do that lookup, but it's kind of easy when we had 4 prefixes, right? We could just step through each of them. The lookup is on the order of is on average the order of the number of entries. But the IPv4 internet is about 1 million prefixes. So every time we get a packet and do a lookup, we would have to look through, on average, 1 million different entries. Scales really poorly. So what we want to look at is how might we use the structure of addresses to be able to improve the efficiency of that lookup. And so we can leverage the fact that there's a tree structure of binary strings. So here we can see we've got every one of these addresses that we were talking about before converted into a binary string, and a mapping of them. And we'll just really think about these 3 bits in the middle because I think if I spend the morning reading out binary strings, it's probably going to be tricky to follow. So let's think about these 3 bits, the blue ones here and the orange ones here, and the mappings that they go to ports. So we'll look here that this is just those 3 bits pulled out. We'll focus on where the differences are in the addresses. That's why we're throwing away the rest of them. And so we have 4 different entries. We have one that starts with 0 and then 2 wildcards. We have a 100, a 101, and a 11, and then a wildcard. So switch to using an asterisk for the wildcard here. And what we can do is we can take those and we can draw those into a binary tree. So we can start out with nothing and then say, well, if the first digit is a 0, take the left-hand branch. If the first digit is a 1, take the right-hand one. And go through these 3 bits and draw the binary tree that describes them all. Then at each point in the tree that we have a forwarding action that we associate with it, we can attach that to that node in the tree. So here you can see this orange node up here. That's where we said, well, it matched a 0, and then there were 2 wildcards. On the right-hand side, well, we didn't have anything that said it was a 1 and matched if there was a 1, then wildcard. We didn't have an entry there, so don't have anything. On the rightmost branch on the 1, well, we did have something that said there was 1, 1, and then a wildcard. So we attached the port 4 action there. And then down on the other branch, we have, well, it was a 0, and then we have exact matches for the 3 bits, the 3 bits there. So we have 2, right at the leaves of the tree, we have 2 forwarding actions that we installed. So that kind of looks like this. If we ignore the bits that didn't have any actions attached to them, then this is what we end up with. We end up with this tree that's got, at different points in it, it's got the forwarding actions that we're going to take there. So now we want to do a prefix match in that tree. So we were saying before that we're going to step through the bits and do a comparison. So here we say, okay, this is 1, 1, 1. So now we walk down the tree from the top. We start say, okay, matches everything. It's got a 1 as the first digit. Then next digit is a 1. And now we've got a wildcard. So this matches this case. So this 1, 1, 1 would go out port 4. So that's and if we were to take something similar in other scenarios, we would, if there were different bits here, we would walk the right branches of the tree. If it just had, anything starting with 0, we would find that port 1 matched that exactly. Then for 100 or 101, we would have exact matches for those. So we can walk down the tree and compare the bits that we're looking at against the actions that we should take. But let's think about this multi-homing case, where we had this network that decided to connect to both Verizon and AT&T. So we didn't just have these, individual actions in the tree. We had ones that potentially overlapped. So our mechanism of walking down the tree and just finding the action that, that exactly matches, that might not be the right one. So let's look at what changes we might make. Because in this case, we've got some prefixes that overlap. If we think about the Verizon case, I'm not going to think about exactly the case. We're just going to add something to our 3-bit example here, keep things simple. And so here we've got port 1 that has got 0, wildcard, and port 5 that's got 001. Obviously, those 2 overlap with each other. So let's think about how we might represent that in the tree. And so what we end up with is just taking the same approach, putting these things in a binary tree, and then going and adding these forwarding actions, still in the tree as they were where they were, but rather than having just one thing in this branch now, one on the left-hand branch, we've got we've got now overlapping entries. We've got 2 entries that could be matched. On the right-hand side, we don't have that overlapping, so we've got the same approach as we had before. So now when we go and look at that packet, we go and take the comparison. We'd still walk down the tree, and we say, okay, it's a 0. Next time, we also hit a 0, so we match that port 1 action. Then we say, okay, well, let's compare the third one. It's a 1. Okay, we found the port 5 action. So for this exact match, we know, okay, we should forward out of port 5. What happens when we get 0, 0, 0? We walk down the tree. We say, okay, there's a 0 here. Let's go to port 1. To that 0 wildcard. It's going to be port 1. We hit a 0, and then we find a node that's got no action associated with it. So, well, in our previous model, if we just look up the exact thing, then we're going to end up in a scenario where we don't know where to forward this packet. So actually, we need to tweak our design a little bit. We need to say, rather than walking down the tree and finding the exact match, walk down the tree, remember the last action that you found, and then if you reach a stage where you don't find an action in that hop, but you match the packet, then use the last action that you remembered. And so that gives you then a way to say, well, in the scenario that you have an exact match, you overwrite the last action when you find the exact match. And when you don't, you just use the action that you previously found. So if we look here, then we would have said, okay, we hit port 1 with 0, 0, 0. We remember port 1. We hit the 0, 0 wildcard. We say, oh, there's not a match here. But that's okay, because we already found port 1. But differently on the right-hand side of the stream, if we take the same thing, if we got to the 1-0 case, the 1-1-0 case, then we might, sorry, there's not a branch here. If we had got to a case where we didn't find a match, we wouldn't have found something earlier in the tree to be able to look at. So we wouldn't necessarily know where to forward that packet. It's only when there is an action associated earlier in the tree. So that's essentially the fundamentals of the longest prefix matching. But it's not the, this case where we have one prefix per port. It's not really typical in the internet. It's not really how things look. Really, we end up with, we've got, even those 288 ports, even if they connect to different people, there's a kind of inherent hierarchy in the network, in the internet, where some networks have routes to a lot of other networks. So you're very likely to get multiple prefixes, because even if you think about my Google example, maybe I got assigned some addresses and I use them all for search. I got assigned some addresses and I use them for YouTube. I might be announcing 2 prefixes. But equally, you might have some overlapping prefixes like our previous example. So we might have several prefixes that are going to route to the same port. So if we draw that out and look at this example, so you can see here they've got 0 wildcard going to port 1, 2 exact matches, 100 going to port 2, 101 going to port 1, and then one wildcard going to port 1. So you see here that most packets go to port 1, other than if they're an exact match when they go to port 2. So if we draw that out on the prefix tree, we will attach, we'll go and pick the right node in the tree. This is the full tree again. And we'll say, okay, 0 wildcard over here, there's port 1. 101, there's port 1 down here. The third port 1 is over on the 11 wildcard. And then our exact match for 100 is over here on port 2. So that would be the way that we can lay that out. This is the layout that we just talked about. We just now pruned the things that didn't have actions associated with them. So same approach we've been taking. But we can think about that in terms of a more compact representation. If we look here, then most actions, the 0 wildcard here, the 1-1 wildcard here, and the 101 here, all go to port 1. And it's only this specific case of 100 that goes to port 2. So we don't really need to have this full representation of the tree. We can think about how to make it more compact. And so we can just say, well, if you match anything, then it's port 1. Any option was down port 1. But now compare the bits down the tree. And if you do find a match in the tree, well, that's where port 2 is. So in this case, we've minimized the size of the tree by not having to store all the different actions to it, by exploiting the fact that we could tell something about how those prefixes are assigned and choosing something that minimizes the number of lookups that we need to do. And so every real router has this longest prefix match functionality. It's an extremely core part of the router. We think a lot about how the efficiency of it is, the memory utilization of it is, because we really want to scale. Like I said, there's about 1 million IPv4 prefixes. You can have more internally as you divide out IP prefixes down, IPv6 prefixes too. So we really want this longest prefix match solution. But this case is one optimization. But there's different optimizations and complexity of solutions that you can take. So we then have various heuristics and optimizations that we can make based on seeing what's actually out there. Like as manufacturers look at what the deployments that they see in the network are, or they observe the global network, or as folks like us do, well, we say, well, we don't need to have exact matches here, or we can exploit the fact that some destinations are more popular than others. We can exploit the fact that some ports on the router have more destinations associated with them. We can think about prefix sizes, because not all. We know that the case is very likely that the internet prefixes can't be longer than /24. So we don't necessarily need to worry about more bits. Same for IPv6. It's very unlikely that we have a prefix longer than a /48 that's going on the internet. So those give us ways to be able to say, well, let's design the way that the LPM lookup works in order to see what we fit in with what we actually see. Another kind of key thing to think about is how quick it is to update. With the control plane and with we're running BGP in the internet. We've got a lot of updates happening, and we need to go and update that tree in order to be able to keep it current with what the state of the actual network is. And so it's not just how quickly, it's not just how quickly we can look up. We also care about how quickly we can update that tree and keep it current with the state of the world. Okay, so we've done some lookups, and we now know what port something should go out of. That's great. That's kind of the core functionality of a router, right? We said at the start that the point of the router is to look up a packet and forward it based on the destination. But that's not all a router does, and these systems are increasingly complex based on the more functionality that you put in them. The kind of basic IP router we just talked about. It has a subset of functionality. It will limit the hardware that you need as well as the software complexity. But there's more and more features that are used in routers to be able to implement different things and different business objectives. And so one of those things is queuing. So rather than just saying, okay, well, we'll take this packet and we'll forward it out this port. And if the port is busy, well, that's bad. We'll have to figure out, we'll just put packets onto the link in whatever order. We might want to think about, well, actually this packet is more important than this other packet. So maybe that customer is paying us more money. Maybe that customer is, maybe that traffic is related to voice traffic, which has a latency bound. I've worked on networks where that certain packets are keeping broadcast TV online and they're very delay sensitive, so they need to be got quickly to the destination. And we don't want to lose them because you lose enough of them and people's TV screens go black and they get pretty unhappy. And so the queuing mechanisms in a line card, which are implemented as a kind of output function, give us ways to be able to, knowing something about the IP packet, to be able to figure out how to send that traffic. And so there's kind of three stages to that. First is classification. I said there, well, maybe this packet's more important than another packet. Maybe this is a voice packet. Maybe this is a TV packet. Well, those things are classification. They're about how do we tell for a packet what queue, what subset of function of forwarding behavior we should put it into. And we might have different strategies for that. We might say, well, this whole port, if a packet came in on port 1, then it's a really important packet. If it came in on port 2, it might be less important. But for other cases, we might want to look and say, well, there's a mix of traffic on this port. Maybe this voice packet is also got some HTTP traffic, some web traffic alongside it. So we might need to look at something that tells us about the packet. And so that might be other fields of the IP header, like the diffserv code point, the DSCP, some fields in the IP header that let us do that marking. We then have some management of the buffers. So we said, well, okay, there's a lot of traffic coming in. Maybe there's two 10 gigabit ports coming in, and we need to forward them out the same 10 gigabit port. Not too much traffic to send to that link. Now we could just put it into some memory, hold on to those packets, and send them if there is capacity. But we have to figure out how to manage that memory. Maybe we want to say, well, we shouldn't let that memory get completely full, or we should reserve some room in case we need to hold on to an important packet. So we end up with some mechanisms on the output line card, on the output decision, to be able to say, like, how do we really classify? How do we really want to deal with the fact that we've got to deal with this packet? We've got too many packets to send via this link, and not use all the memory in a uniform way. So that buffer management is another thing. And then the third part of queuing is scheduling. So now we've got all these packets in memory. How do we choose what order to send them out? If we had different packets, then we should maybe, like, if we'd had different queues, maybe the voice packets are really important, and we should get to those first. They really are delay sensitive, so we need to get them out onto the wire as quickly as possible. Maybe other packets we don't come to till later on. Maybe they're more delay tolerant. Equally, should we let all the voice traffic go, or should we drop some of that? Should we say there's no capacity for the web traffic? Those different classifications and different scheduling behaviors of how to put the packets on the wire, again, introduce complexity into the router. And you can kind of see here that we talked about, well, look, we don't have very much time to do very many cycles to do these functions. The more things that we introduce that the router needs to do, likely the fewer packets it can forward. Or the more cycles we'll need, like the less capacity it's going to end up with. We maybe have the same chip, but it can't do as many ports it's got to do because it's doing more operations per packet. So the overall complexity of these systems especially because they're designed to work in many different deployments, ends up being pretty high. And so some of the advances in the capacity are to do with limiting that functionality. Today, Google doesn't. On the internet, essentially, the question was, I'll just repeat it. It was, who gets to set the DSCP bits? Who gets to say the classification of a packet? Now, on the internet, we essentially just don't trust anybody, right? If you can send me a packet and tell me it's really important, well, it's really important to you, but is it really important to me? Probably not. Or maybe it's not. So what we do is we bleach the packet. Anything that comes in, we rewrite all the bits to 0, and we say, sorry, it's just as important as every other packet, no matter what you thought about it. So there's not really any idea of this kind of differentiated services on the internet. Now, I've worked at providers that are selling private networks to people, and so if I have a customer they're running their office network, and I'm providing interconnection, then they can pay me and say, well, actually, this voice packet is more important than another. So in those scenarios, that's where you might allow the customer to set the marking, and they would choose, well, this packet's really important to me, but it ends up being part of the service that you sell. So if the service is basic internet connectivity, usually you don't have any ability to do this control. And but in private networks or in more premium products, in the way the industry would have historically looked at them, you get to choose them. Now, a lot of these things are really to deal with not having engineered a solution to work on the internet. So, services like Skype. Well, people said, well, I get actually better voice quality here via Skype than I got from my phone line. So why wouldn't I just use Skype? And Skype was engineered in terms of the codecs it uses, in terms of the encoding it's using in the packet to work well without having this prioritization. The kind of historical phone networks that we're doing weren't engineered that way. And so it's becoming increasingly irrelevant, I would say, to have this kind of prioritization. But it's often used as a way to manage priority between different bits of the business. So when I was at British Telecom, for example, then if you were a commercial customer, a business customer, then you were more important on the core network than you were if it was a home broadband customer. So that kind of business priority is enforced rather than letting the customer sort of differentiate their traffic. So this being said, a long aside to say there are many complexities that come in. That's one of them, kind of mentioned throughout. There's also a few other things that might make this more complex. Especially where we're not just forwarding a packet based on its destination. We're doing more actions. We're maybe having to take headers off the packet because it's got more stacks of headers on it. Other things like that. We might need to do more, but we're just going to assume the kind of simplest possible picture, which is there is no classification. Every packet is important as every other one. We'll deal with buffer management in the time-honored tradition of if it's full, we'll just drop it. So we call that drop tail dropping. So if it's full, there's no room for us to store this packet, the link's full, so we can't immediately put it onto the packet, well, just throw it on the floor. And then we'll think about a FIFO scheduler. So the first packet that turned up is the first packet that we send. And that just gives us the simplest possible setup to be able to think about forwarding. And as I kind of described through a couple of the answers there, then there's just many complex scenarios here. And they're really used to kind of implement some of these business objectives that we have for the networks that we run. That aren't just forward packets as fast as possible. They're forward packets and think about the service a little bit. And that's where queuing comes in. So, to recap. Talked about routers. They have different planes. We talked about the 3 different planes. The control plane, that's used for programming the forwarding entries. And dealing with exception packets. So that's where we're running our routing protocols. We're telling the forwarding plane, the data plane what to do. We have the management plane, the oft-neglected interfacing with the device, telling it what to do, who it is, and hearing from it what's going on in the network for us to be able to know what the network is running like. And then the data plane, which is really the thing that we want from a router, the packet forwarding. The data plane itself leverages those trade-offs in software and hardware. Where we can use hardware we can live with the inflexibility, but we get the speed. Then we use that hardware. We have dedicated forwarding chips that are doing that. But where we need flexibility, we end up with software, but we have to deal with the fact that it's slower. And the main data plane challenge is this speed. We want to scale to those systems that are 230 terabits per second, and next year will be 400 terabits per second, or in a few years will be 400 terabits per second. We want to deal with that, so we need to be really, really efficient in terms of packet processing. And really, updating the packet header, the things that we restrict ourselves to, it's pretty easy in hardware. But the LPM lookup, the real forwarding of packets according to those routes that were installed, those IP routes that were installed, that's the more difficult bit. And that's where we kind of talk through the LPM process, the longest prefix match process. So, unexpectedly, we did not use the whole time. So, questions? Hey. Yes, usually. So how this kind of actually ends up tending to work is that you have the fairly fast first processing, the breaking down of the packet, get into the chip and the forwarding chip. And in this case, we just needed to do an LPM lookup. We just need to do one lookup. But sometimes we have to do multiple lookups in different databases to be able to figure things out. So that's really where the core of the cycles end up being spent. The fabric part is also quick. So the real constraint when we're looking at these routers is usually about, well, how fast can that chip go and do the functionality that it needs per packet? And we look at that and we think about, well, how many packets are going to arrive? And why we talk about things like the size of the packet is because a 400 gigabit link that's got 1500 byte packets is many fewer packets than if they're 64 byte packets. So what we do is we spend essentially a fixed amount of time per header of a packet, not the size of the packet. So we really care about when we're talking and doing some of these design analyses on these forwarding chips, we're saying, well, at 200 byte average packet size, we can achieve this rate. And so that's where sometimes the number we talked about, the capacity, the R number of speed per link, might not actually be the number that you saw on the line rate. It might be lower than that. It's like the little Linksys router I put up. There's no way that thing can forward at 1.4 gigabits per second because it's doing a lot of things in software. So even though you could give it 1.4 gigabits per second of traffic, it's just not doing it because it's spending a lot more time in the lookup phase and in the lookup phase and in the forwarding than it would need to do to sustain that line rate. Sure, on the right hand side. So historically, yep, how that works is, so this is an internet interconnection. It's called peering. It's when two networks connect to each other. And there's a few different ways that they work. One is that you buy from somebody else. So I go to a provider and I say, hey, level 3, I want to buy access to the internet. And they sell me access to all of the internet. And they charge me for that link. But then there's also connections where I say to, maybe I say to Verizon or I say to Sonic or some ISP here, and I say, hey, I'm Google, I'd like to send you traffic for YouTube, and I'd like it not to pay for it, thank you. And you'd like not to pay for it. So we have a bit of negotiation, and we say, okay, yep, great, we'll interconnect with each other privately. And how that tends to work is that then we agree where it's going to be. Maybe we'll do it in multiple places across the country, and we'll go and then, somebody goes and physically plugs in a cable. One of the things we've done at Google and why we've spent so much time in the management place, we have a lot of links like that. Thousands of links like that. And they all need capacity upgrading things. So we've actually worked on a way that that's software automated. So a lot of the time when somebody comes and asks us for a link, the first time it really reaches a human is when the human is plugging something in. And then everything else is machine-driven or robot-driven from there. But there's kind of the commercial negotiations that go into it, and then the practical, technically setting it up. And why the management plane is really important in this space is because someone needs to tell it, we've got this link is going to go between, Sonic and Google or AT&T and Google. We're going to run BGP on it. So we have to tell the router what to be doing in terms of control plane protocols on those links too. Sure. Yeah, so that's why we're kind of picking the simplest possible model. There's a lot of sort of ways that we think about how to manage that buffer occupancy. So you might take that into account. Even if there was just a single class, you might say, well, I don't want to be full. And some things like TCP, well, it's better if I drop some packets and they back off and they don't keep sending me. So you might do randomly dropping packets before the buffer was completely full. But then if you've got different classifications, you might say, well, why would I want to drop this really important packet before I drop this other one? So you have a weighted random early detect, that's what we call the random dropping, that gives you a way to manage that buffer to say, okay, well, the buffer can be this full of these packets, and if it gets greater than this amount of full, then start dropping those packets, and you end up with these slopes that kind of give you a complex algorithm to say, based on the classification, how should I use the memory that's available to me? Sure.
You mentioned these clarifications that you don't know what to do with the packet or you don't know where to send it and you just drop it. Is it like ever better to flood the content?
No. I think that there are local networks where flooding when you don't know what to do is okay. Like you might learn, there's some learning. But in IP routing, we don't do that learning, right? We don't look and say, well, I saw this packet on this port, so therefore it must live, like that address lives over there. We have the control plane protocols to deal with it. So what would happen if we flood the packet? Well, probably we send out the same port we just got it in. And the guy on the other side, or the router on the other side would say, well, yeah, you should be forwarding that. And so then we end up with routing loops. So like where we just have routers or different parts of networks that are just passing the same packet backwards and forwards until the TTL expires. Why the TTL is really important, right? We don't want that infinitely going around. But no, in general, we want to drop the packet. It's usually a good signal. And if you don't want to drop the packet, that's why you have the default route. That's so when your laptop is connected to a network, well, it doesn't need to know about the whole internet, right? And if we think about it, it just needs to know, well, it's over, like the internet is via that router over there. So the next hop for everything is set to the default route. And so if you don't want to drop a packet and you want to have somebody else handle it for you, then the default route gives you that, rather than flooding. That depends on the hardware. So and this is somewhere else where we make hardware trade-offs. So if we're thinking about the kind of chips that we might be building and talking about doing 400 gigabits per second on 36 ports, or maybe there's 2 chips per line card, so 18 ports, then 8 buckets per port is probably normal. But if we think about something that takes in some device that connects a lot of broadband subscribers, a lot of homes to it, then in that case we've got lots of individual subscribers, lots of individuals that are all connected to the same thing, and we might want to classify between them. So at that point we can get up to 256,000 classifications per port. And what does that come with? Well, it comes with a bunch more memory, it comes with a bunch more complexity for managing them, and so that then means that the complexity of the line card goes up. Usually what that means is then the throughput goes down, because we've got much more to do per packet. But also we just used a bunch of we've essentially got something that's probably 60 centimeters by 40 centimeters, 2 feet by a foot and a half-ish. That's the whole amount of PCB that we can deal with. So the more things that we put on it that are doing not forwarding, the less forwarding we do. And so the density, the kind of capacity of those routers tends to be lower. But in those cases, we can end up with extremely complex scenarios, and they're usually in this kind of subscriber management where we're dealing with individuals rather than ports. Now, if you're internet network, you're really only dealing with ports, and you're probably dealing with one class per port, so you maybe don't even use those. Internally to a network like Google's, though, we have different things that are on the network. We have net traffic that's to do with copying between machines. Well, maybe they can just come back when the network's less busy. But then we have traffic that's, you did a search on google.com, and you get really annoyed if we don't deliver that. So we want that to be more important than others. So that's where we have some level of classification, even though we're carrying just internet traffic. In that case, it's our business objective.
You mentioned that number of processing one packet in 5 nanoseconds and kind of trying to increase rate. And with the line rate, even if this number is going to get lower, which is pretty impressive and unbelievable. But in a way, processing the packet headers is easy spotting all of this, right? do with the body of this RAID, or do you just parallelize? Like, how do you?
I make the joke that I don't know what's past the headers of the packet. Like for routing, we don't care. So we for sticking for these like IP routers where we're doing layer 3 forwarding only, we just look at the headers. Anything else there, it actually is great if it's bigger, right? Because that means that we get some more, get fewer of the packets per time. But these systems really, they might be able to do some looking into the packet, but they really don't. We really don't want to get involved in that because we really want IP to be transparent to what people do on top of it. So what we do tend to look at sometimes is we look at, like, we say, oh, this is IP, but actually inside it's got TCP. And we want to look at things like the source and destination port, but we usually use that for entropy when we're trying to like, you can imagine that, we didn't really mention it here, but you can have a route that goes via 2 different ports, and we want to figure out how to share, like, load balance traffic across the 2 different ports. So we might look a little bit into the header. We generally try not to. So, and then if you're trying to do things at line rate, at 400 gigabit line rate, extremely unlikely that you can do anything with the header. So when you see things that do firewalls, which might need to look further, the more complex they get, the less capacity they end up being. And we might be able to do some things here, like we might be able to do what we call access control lists. So that's where, like, we don't allow any packet that has TCP port 147. I don't know what TCP 147 is, but apparently we're going to drop it. So in that scenario, we would say, okay, there's this offset into the packet. If you match that this is a TCP protocol in the IP header, then look at this offset in the packet, which is the port number, and drop it. So we can do those kind of simple kind of equality checks. But it's another thing that comes at some cost. Actually, what we end up doing is having more hardware and a lookup table to be able to do those kind of exact match lookup tables earlier in the process. And so it's another place where the more complex you want those inspection of the packet to be, either the more complex you make the router, which probably comes at the cost of capacity, or you just say, well, I don't do them, and I hand it to something else that goes slower to be able to do that more complex functionality. But yeah, we don't really look at the packet header at all, past the packet headers at all. Sure.
How common is it that a buffer will completely fill up and you actually need to drop packets? Is it a common occurrence, or?
Good question. It depends on your capacity planning approach. So when we look at the network, what are we really doing? Well, we're building a graph. It's got a bunch of nodes, it's got a bunch of edges, and then we've got some demands on the graph. So the demands are where the traffic's coming from and where it's going to. And so what we'll do is we say, well, we think that there's going to be this much traffic coming in New York, and we think it's going to be served out of this data center in Tulsa, Oklahoma. And so we then build enough capacity. And so if we built enough capacity, well, it shouldn't get full. But if we haven't, then it does. And then you can then say, well, do I build all the capacity that I have to? So I could go and build, like every time I could think about those guys in search over there. They really want to copy these big amounts of data apart, across the network. So I should always have the capacity available to do them. Equally, it can be a bit smarter and say, well, rather than giving them completely all the capacity that they want, because TCP will ramp up and try and use as much as it can, I can say, well, I'm only going to give it this much. Like I'm just going to capacity plan that they can do 200 gigabits a second of copy traffic from Tulsa, Oklahoma to Council Bluffs, Iowa. These are the kind of places that Google has data centers that I, as a Brit, was not aware of beforehand. Have been to Council Bluffs, Iowa multiple times, which is not a sentence I ever thought I would say. Nothing against it, I just hadn't heard of it. So in this scenario, we've got we didn't necessarily build all the capacity for them to do that kind of copying of traffic. So in that case, we do have pretty full buffers because someone's trying to use all the capacity possible. And one of the metrics that we look at in the networks that we build is, because we're trying to build these scales that are really, really challenging. We're looking at 400 gigabit ports. We've already got them. We're looking at 800 gigabit ports. They're not being produced yet, but we're already planning on them being there. So we're always at the edge of trying to get the maximum capacity that we can. And so we want to use that asset as well as we can. So we're really trying to say, if the network's 100% full, that's awesome. Because then we're really using that infrastructure that we built as efficiently as possible. So for us, they're pretty full. But in other networks that I've worked in, we had lots of business customers. They're paying a bunch, and they pay us for 10 gigabits of capacity, but they just never use it. But they want it there just in case. And so in that case, those networks had extremely low utilization. And so it really depends on what the network looks like and how much of it you build, if you can scale above something, and then how you want to manage traffic on it. So it's kind of an overall view of both the service you're trying to provide. Like your broadband network provider probably says, well, on average, a user uses about this much traffic, so I'll build the network according to this with some error margin. But like what we used to worry about in the UK was we got streaming deal for soccer, football. That one took some lookup, and it wasn't order one. Everyone, at that point, everyone's watching these games on YouTube or on our streaming service, and so we just hadn't built enough capacity for it. So there's just different types of network have different times where it is. Usually, internet traffic is kind of diurnal, so you end up with like a spike at some point, and then two spikes a day, basically. Business traffic tends to offset, so you can do tricks like how much of the network do I build based on these different customers, and sort of overlay the two to get the best utilization out of the network. But it's fairly common that we're dropping packets. Even just spikes of traffic make it happen. There's some statistic where I've looked, we have a counter for all the traffic we're dropping in Google, and that is more traffic than some networks I've worked on. I can't give you what the numbers are, but you would be surprised how many packets Google isn't carrying that we maybe could. Sure. Yes, so essentially when I'm talking about that, it's internal business. It might be an internal business decision. So when I was at British Telecom, for example, we'd have business customers and consumer customers. But that said, well, all internet traffic is the same because it's based on the customer, right? It doesn't matter who's sending the packet; it's to do with them. But the net neutrality discussion is about, well, if I have ways to be able to classify traffic internally to my network, how do I choose to drop them? And one thing you could say is, well, if someone comes along and pays me more, then I'll carry their traffic. And so you have to pay me. Now, that has implications. So it has implications for how the internet's work. Like, if Netflix had got charged, or YouTube had got charged for every time that it tried to do these startups would never have produced a service because they would never have been able to afford to have a decent quality service. And so it's extremely intertwined between the how to classify packets and then the commercial negotiations around them that then has these regulatory implications. I think my observation is telcos the people that provide broadband networks, like to be, say, oh, it's really hard, right? We have to carry all this traffic. People keep sending all this traffic. But what are your customers doing? They're buying an internet connection so they can get all that traffic. So your commercial model should probably work. Like your product is being sold based on the fact that there is like YouTube or those kind of things available. So the whole practice is an interesting discussion about who's perceived to be taking the value out of out of internet connectivity, and the classification really is the technical means by which you could do that, which honestly is a footnote on a footnote of the whole discussion. Hi.
So I guess I like that, like the increase, like throughput, but I was wondering if there's any like DDoS protection built into the network for like the private DDoS, like somewhere DDoS that actually like cut off the DDoS.
Yeah, so essentially you end up with, in most networks that see this, which is essentially every network these days, some mechanism by which you mitigate those DDoS attacks. So you have an attack, and there's it's the similar thing to this queuing thing, right? We have to be able to classify it. Let's say, what is the DDoS attack? What does it look like? And then we want to be able to say, well, where can we drop that? And now the ideal is you drop it outside of your network. Maybe not possible. Some places you can kind of ask an upstream provider, so signal to them, hey, I don't actually want traffic to this destination address. But in that case, you're saying per destination address, so you've kept the lookup complexity just on the destination address. Then maybe at the edge of your network, you say, okay, well, same thing, I could make the same destination-based thing. Maybe I could do a simple port-based one. Like if you're trying to DDoS something in Google and you're sending just a port, same destination IP and a single port, Well, we can probably filter that in the complexity of the routers. But above that, we need something that can look into the body of the packet to be able to do more classification. And so in that case, it tends to be that you have we call them scrubbing services or mitigation services, where you say, well, any traffic that's going to somewhere that is getting DDoSed, like DDoSed, redirect it to some other service that is more capable of being able to look into the packet and probably do that in a parallel way, because I think that, the numbers these days for these kind of attacks are mind-blowingly astronomical. And so that's then how you end up with that mitigation. Now, at the end of the day, like if you send more traffic than there is input capacity, there's not much we can do, because you've already dropped the packet on the other side of the link before you could even do anything with it. And so that's part of the capacity planning process. Sometimes you're already trying to build these networks to be reliable. So if we want 100 gigabit of capacity into another network, well, we're definitely building 200 gigabits because all kinds of things could fail on those links. So we've got some bulk there, but at some point you essentially run out. You potentially run out of capacity, and that's one of the challenges about dealing with attack traffic like that, is to be able to say, well, how much capacity do I want to build ahead of time, increasing my cost, the cost of my network, increasing the number of things I have to manage, to be able to absorb something that might rarely happen. And when you see somebody get kind of knocked offline through this, it's generally because they ran out of either scrubbing capacity or they ran out of link capacity into the network. It's actually quite an involved set of interactions between networks to figure out how to help mitigate those kind of scenarios.
We're actually out of time, so if anyone has any follow-up questions, you can post them on the end thread, and we'll pass them along to Rob. But with that, a big thank you to Rob.
Thank you very much.